developer of methods, and it's always a constant motive of inspiration for all discussion that we have about fluorescent and research. So today, Dave Jason is gonna talk about an introduction of time-resolved fluorescence, and in particular, he will make a case about the phasors that we will extend along the whole day. So I would like to welcome all of you to the second day of the advanced workshop, and I'm passing the word to Dave.
Okay, thank you very much. It's a pleasure to be here again. I'm happy to say that I did wake up at 2 a.m. again today. I don't know that this will continue every day, but so far so good. It's even too early for my coffee, so I'll get that later during one of the breaks. So yes, today is going to be a complete time-resolved fluorescence day, I think, and so I thought it's appropriate to introduce you to some of the concepts. Some of you may be familiar, some not, but I want to take you along on that journey. So we might ask ourselves, actually, why do fluorescence measurements? And one of the big reasons is that fluorescence intensity measurements are what we call extensive properties. This means they depend on instrumentation parameters, how much light, how good the detector is, etc., and the concentration of the fluorophore. But lifetime measurements are intensive, which means they do not depend on instrument parameters or the concentration of the fluorophore. The lifetime is characteristic of the probe itself. This intensive property is extremely important for many in vivo measurements, as you're going to learn during this course. Now, many fluorescence intensity-based assays for different ions like calcium, etc., require ratiometric determinations. I mentioned that a little bit when I mentioned calcium probes yesterday. That is, you need to do intensities at two different excitation or emission wavelengths in order to quantify how much material is in there. But lifetime data can be used at a single excitation or emission wavelength because of this intensive property. And you need lifetimes also to quantify certain types of fluorescence measurements, such as anisotropy polarization, quenching, and certainly Forster resonance energy transfer, which will be a big focus of this course. At a more fundamental level, lifetime determinations are often required to understand the photophysics of fluorophores in different environments. So I'm not going to go into a big history thing. I'll do that on Thursday, but it is interesting that one of the first really seminal papers was by George Stokes, who was the first to really start to grasp the meaning of fluorescence phenomena. And I'll tell you more about this paper on Thursday. But it's interesting that he says he obviously wondered about this possibility of a time between excitation and emission. He said there's nothing to create the least suspicion of any appreciable duration, but then I like this part. I've not attempted to determine whether any appreciable duration could be made out by means of a revolving mirror. And I think it's lucky for him he didn't try this, because he'd have to rotate that mirror awfully, awfully fast. And the first serious attempt to measure fluorescent lifetimes, which I'll talk in more detail on Thursday, this paper by the famous American physicist Robert W. Wood. And I like the title, The Time Interval Between Absorption and Emission of Light and Fluorescence. But the first successful attempt to measure lifetimes, that is, the first actual measurement, was by Enrique Gaviola, famous Argentine physicist who did his studies in Germany and his training in Germany in the 20s. And he wrote this paper, Ein Fluorometer, for measuring the lifetime. And that's why, actually, Gregorio Weber explained to me, when you're talking about an instrument to measure lifetimes, you call it a fluorometer with an O. If it's an instrument to measure spectra, you call it fluorimeter with an I. So that's really the origin of the difference. Well, time-resolved data is typically obtained using one of two methods, time domain or frequency domain. And we're going to talk briefly about each of these approaches. And phasors, as I'll mention this now and then later, they can be constructed using either time domain or frequency domain data. And some people have this misunderstanding that, oh, you need frequency domain to do phasors. That's not the case at all. So in the time domain, also called the impulse method, the sample is illuminated with a short pulse of light, and then the intensity of the emission versus time is recorded as shown in this picture. Originally, these very short pulses were generated using what we call flash lamps, and they actually had widths on the order of several nanoseconds. So we would consider this to be really, really a broad, long pulse today. But back then, they were pretty good. And modern laser sources can routinely generate pulses now with widths on the order of picoseconds or even shorter, femtoseconds. And we see from the diagram that you excite a population of fluorophores, whether it's in a cuvette or in a cell or whatever. You can even do single molecule work now, but that's another story. And then you look at the intensity of the fluorescence decay with time. And when that intensity decays to 1 over E of the original starting value, that is 36.8%, that's the time we call the lifetime. So the intensity versus time is given by this relation. T sub t is equal to alpha, the pre-exponential term, times e to the minus t over tau. Tau is the lifetime. And especially for many years, it's been more common to see fluorescence decay data displayed using a logarithmic plot, because in a logarithmic plot, you see it's a straight line if it's a single exponential decay. And in fact, when I was a student, I even did a little bit of time domain data, I'm embarrassed to say. No, that's fine if you do that. And one of the reasons we would put these on graph papers was to get a better idea if it really was a single exponential. Now with computers, you don't need to do that. What if it's not a single exponential, which unfortunately is by far the majority of the time? You don't have single exponentials. Sometimes you do, that's good. And then you have an expression that has the sum of the different pre-exponentials and lifetimes of the various components. And in this case, you might get data such as this sketch below. So here, in this is still the log intensity. We see at least two lifetime components indicated tau 1 and tau 2. And we can see we no longer have a straight line. So it was very easy when you plot on a log scale to see if it's not single exponential. This is oversimplified, but it illustrates the point. Now here's actual data to illustrate this point further, taken with anthracene in a time-correlated single photon counting instrument. I'll talk about that method in a moment. With a light-emitting diode, a short diode excitation source. And we can see the plot intensities on a log scale. Our maximum here is about 10,000 counts. And on the time scale, we have channels, which are 56 picoseconds per channel. And the data points are the red points, and then the solid line through them is the best fit. Now, you fit a model, and then you test the data to your model, and that's illustrated. That gives you what's called the chi-squared value, and it's illustrated below, where we see the straight line is the actual best fit, and then we see the scatter of the data points above and below that. So when you get a nice flat curve like that, that's a good fit. But how do we get to 4 nanoseconds? Well, this is 36.8% in the log scale. And from the start, the maximum, we went 73 channels. So it's then 73 times 0.056 nanoseconds per channel, 4.1. So that illustrates more practically how this is accomplished in the lab. So what is this time correlated single photon counting method, which is probably the most popular pulse lifetime method out there? Well, you have a pulse light source, and then either with electronics or even with a phototube, you monitor when that emits the pulse of light. And this information is fed into the start input of what's called the time amplitude converter. And this device will start when it receives the start pulse. It starts to develop a voltage ramp for the output, and you get more and more voltage as time goes by. Now your exciting light hits the sample, and then looking through filters or monochrometers or whatever, and also very important, you have to reduce the intensity to 1 photon per pulse. So that's why it's single photon counting. Then you get a photon when you have an emission event detected. And that goes into the TAC and it stops it. And now you have a voltage registered for that photon event, which goes into called a multi-channel analyzer, a computer, let's say, and it marks that event. So here I show what would happen. You get the first photon and it goes into one channel. Then the second photon, a different channel. And the third photon, different, and so on and so on. And finally, even after 17 photons here, you begin to see we're getting what looks like a decay process. And you do that over and over again, typically to get thousands of photons. In the data I showed you, it was typical in these instruments to go up to 10,000 counts. You want to get enough data to get good statistics. Well, that's the time domain. What about the harmonic or the frequency domain, also called phase and modulation? Well, traditionally you use a continuous light source, such as a laser or even a xenon arc, and the intensity of the light source can be modulated sinusoidally at high frequencies, as shown here. So the light that hits the sample, before it hits the sample, you have a way to modulate the intensity sinusoidally. And you can use a continuous light source and then use some device like a Paco cell to modulate that. Or nowadays you also have light emitting diodes or laser diodes that can be directly modulated. So you don't need an external device to modulate the light. So at any rate, you get sinusoidally modulated light. So in such a case, the excitation function can be described as a function of time of E0, the intensity at time 0, times 1 plus ME, and I'll talk more about ME, the modulation factor, sine omega tau, where omega is the angular modulation frequency. Now, it's important to realize for these discussions that omega is 2 pi f, where f is the linear modulation frequency. So when you hear someone talk about the modulation frequency, actually Leonel mentioned a little bit the other day on some of his light sources, he's talking about the linear modulation frequency. The equations, we talk about the angular modulation frequency. Now, due to the persistence of the excited state, once you excite the fluorophore, this gives rise to an emission that's modulated, but it's shifted in phase relative to the exciting light as shown here. So we see in blue the excitation goes up sinusoidally and down. And as it's going up, we start to see the emission go up. And then it also goes down, but it never comes down as far as deep as the excitation, because it starts getting pumped up again, as you see. See, it gets pumped up. But you have a delay in phase, or a phase shift between the excitation and emission. Okay. In addition, you get a change in the AC/DC levels associated. So the DC level we call just the average value here of the center point of these modulated curves. And the AC level is how far you go above and below. And you can see that actually the AC to DC ratio is different for the excitation than the emission. You never come down have as much modulation in the emission. Well, this is important because, as we'll see in a moment, you can demonstrate that the trace of the fluorescence with time is F0, 1 plus modulation, an AC-DC ratio of the emission times sine omega t plus phi, where that's the phase angle of the delay. And it was shown in 1936, actually, by Dushinsky, that the tangent in this type of excitation, the tangent of the phase angle, the phase shift is equal to omega tau. Now, the modulations of the excitation and emission are given by these expressions, just the AC to DC of the excitation and the AC to DC ratio of the emission. The relative modulation is then the ratio of these modulations for the fluorescence over the excitation. And in fact, tau can also be determined from modulation according to the relation. The relative modulation is 1 over the square root of 1 plus omega tau squared. So these are two independent measurements I want to stress. You can measure the lifetime with the phase or the modulation. Typically, you measure both. So if a fluorescence decay is a single exponential, the important point is tau phase and tau modulation will be identical. They'll be equal at all modulation frequencies. If the decay is multi-exponential, though, tau phase will be less than tau modulation, except in special case we'll mention later. Moreover, the values of tau phase and tau modulation will depend on the modulation frequency. So the higher the light modulation frequency, the lower the tau phase, tau modulation will be. So to get a feeling for this, let's look at this data set. So we see a linear modulation frequency of 5 megahertz. And in this sample, I'll tell you what the sample is on the next slide. We see 6.76 measured nanoseconds measured for phase and 10.24 measured for modulation. Immediately you see this is not a single exponential decay. They're not identical. Indeed, as we increase the light modulation frequency, 10, 30, 70 megahertz, the phase lifetime gets shorter and shorter, and the modulation lifetime gets shorter and shorter. Well, it's the difference between these tau phase and tau modulations with frequencies that forms the basis of the methods used to analyze for the lifetime heterogeneity. In other words, what are the lifetime components and what are their relative amplitudes? Now, in the case I just showed, the actual system being measured was a mixture of two fluorophores, which I mixed in the lab, of 12.08 nanoseconds and 1.38 nanoseconds. And the relative contributions to the total intensity were 53% and 47% respectively. Obviously, I was shooting for 50-50. That's as good as I could get. But here I want to distinguish. And this is important because, believe me, in the early years of lifetime measurement, this did cause a lot of confusion. We want to distinguish between the fractional contribution of the total intensity, indicated as F, that's what I'm talking about above, 53% of the total intensity or 47%. That is the total number, the fraction of the number of photons hitting the phototube, and alpha, the pre-exponential term. The relationship between these two terms is given by this expression. The fractional intensity of the ith component is equal to the pre-exponential of the ith times the lifetime of the ith over the sum. And in fact, pre-exponentials are telling you how many molecules are there, but the fractional intensity is telling you how many photons from these molecules reach the phototube. So in this case, the ratio of the pre-exponentials, in this case, was about 1/8. In other words, there were 8 times as many molecules in this solution with the 1.38 nanosecond lifetime as there were molecules with the 12.08 nanosecond lifetime. And it was especially common, and still is common, for people reporting time domain data to give the pre-exponential factor. those of us doing frequency domain would traditionally give the fractional intensity, and there were a couple of famous cases that I don't have time to go into now, where this caused quite a lot of confusion for a while until we finally figured out, of course, we're being stupid. This is just how we express it. So this is how frequency domain data is presented normally. You plot the phase delay, this is the blue circles, or the modulation ratios, the red squares, as a function of modulation frequency, the linear modulation frequency of the light. And we see the phase delay goes from 0 to 90 degrees. Modulation ratio can start at 1 and go down to 0. This is showing the fit for fluorescein in a cuvette, in a ISS lifetime machine. And the data is best fitted here by a single exponential of 4 nanoseconds. So you put all the data points up, and then you fit the phase delay or the modulation ratio to different models of single or multiple lifetime components in different amplitudes or fractions. And when you've worked with this for many years, to your eye, you can look and see, oh, that's a single exponential decay in the frequency domain, or at least I know Enrico can do that with his eye. Well, what if you have different lifetimes? Well, this shows that lithium bromide free, the blue things, the blue dots in squares, at 1.74 nanoseconds. And we see we have to go to higher frequencies to start to get an appreciable phase delay. When it's bound to transfer RNA, it's single exponential 27 nanosecond, and it shifts to lower frequency. So these curves, if you look at the phase data for the 27 and the 1.74, they're actually superimposable if you were to shift them along the frequency domain, the frequency axis. But they're just shifted. What if we have a mixture? Well, here we see the blue and the black curves are due to one component, 4.05 nanoseconds, and the red and the green are phase and modulation for a two-component system, where we have 50% 4.05 and 50% 1 nanosecond. And with your eye, you can probably already tell that those curves are not superimposable. There is a difference in the shape. But again, you would fit the data to the multiple components and extract the what you want. And just as another point, frequency domain and domain data can also be acquired using the harmonic content of both sources. So you don't have to sinusoidally modulate the light. If you have a pulse source, repetitive pulse source, if you do a Fourier transform, you can get the harmonic content that would give rise to those pulses. And this is actually in a paper I did with Enrico where we did synchrotron radiation as the light source. And this is gives these pulses as these bunch of electrons go around this big electron storage ring. But you get these light pulses, and you can generate the frequency domain data from that. In fact, in laboratories such as Enrico's, he has a number of FLIM microscopes. I don't know how many now, but a lot. And some do time domain pulses, and some do frequency domain. And as an operator of the instrument, and maybe you'll see this, you don't care what it is. You just get the lifetime. It's all the same. Well, now let's talk about phasors. Actually, the concept of phasors has been around for a long time. The original phasor transform was an invention of Charles Steinmetz, who was a mathematician and engineer born in 1865. And in the last part of the 1800s, he was actually a famous figure in science and technology and made significant contributions to electrical engineering and knew a lot of the other big scientists. There he is with Einstein. He knew Edison, of course, and he was quite a known popular figure back then, and did important contributions, as I said, to electrical engineering, and spent the last part of his life working in General Electric in Schenectady, New York, actually. Now, he introduced the concept of phase vectors, which he named phasors, in a paper he published in 1893. There's the reference down there. And specifically, his phasor transforms greatly facilitated analysis of electrical circuits, like specifically resistance, inductance, and capacitance circuits, such as shown in the left there. And this allowed algebraic equations in phasor space to be used to analyze these circuits for their outputs, inputs, etc., instead of differential equations in the time domain. And it really was a significant mathematical tool to use to analyze, and hopefully we'll see this same concept can be used in lifetime measurement. I think Enrico's told me he used to teach many times phasor diagrams in electrical engineering back in physics courses. In fact, if you search phasors in PubMed, you'll pull up a lot of electrical engineering papers too, so you have to be careful. Now, the inspiration for phasors in fluorescence was actually due to a concept introduced by Gregorio Weber. And again, we'll learn much more about Weber on Thursday. And he wrote this paper, Resolution of Lifetime Components in a Heterogeneous System by Phase and Modulation. Because the problem at the time was we had, back in Weber's lab, we had 2 and then finally 3 frequencies, but it was laborious to try to figure out what the components were that gave rise to those phase and modulation measurements. And after a big effort with a lot of difficult mathematics, Gregorio Weber came up with an approach to do this for n components if you have n frequencies. And along the way, he developed these terms for the frequency domain and the time domain. And those G and S terms are the terms we use in the phasor plot. And in frequency domain, you see the G, which you'll see is plotted along the x-axis, is the modulation times the cosine of the phase shift, and the sine is the modulation and the sine of the phase. The S is the modulation and the sine of the phase shift. But he also pointed out that you can get these terms whether you're in the frequency or the time domain. So that concept goes back to Gregorio Weber's paper. Now, the first use of the phasors in fluorescence appeared in this review by Enrico and myself and Bob Hall, a student of Weber's, in this appendix. And there you see a modern phasor diagram, and you're going to see a lot of these in the course where we have the S and the G plotted. Now, the original motivation for this phasor plot was to provide a relatively simple demonstration of why in a mixture of 2 fluorophores, each with a single exponential decay, but one lifetime shorter than the others, the phase lifetime will always be less than the modulation lifetime. And to make this point algebraically is very, very complicated, but you can do it relatively simply using trigonometry in the phasor plot. And this was also in the paper to show why the phase would be less than the modulation. And trust me, this is much simpler than any other way to do it. And just as an aside, and I think interestingly, a few years later in her master's thesis in 1988, Carolina Julian from Catholic University of Valparaiso, who visited my lab, gave the trigonometric explanation using the phasor plot for the case of excited state reactions, which result in a lengthening of the phase lifetime compared to the modulation. And I'm going to mention that in my lecture today, and it's very important. But she was the first one, I think, to ever make this diagram. And here actually is Carolina and Susanna Sanchez, one of our instructors, visiting my lab in Dallas at that time, and my technician, Vicki Thomas. And as you see, Susanna hasn't changed a bit over the 35 years, so good for her. So what was the first use of phasors in the laboratory? Well, I think it was this paper with Greg Reinhardt, Pasquina Marzola, myself, and Enrico. And here we see Greg and I terrorizing the neighborhood with our motorcycles back in those days. And this was to describe a method using phasors to do online background subtraction. Why do this? Well, this gets back to the concept that Enrico can tell you these time domain, frequency domain wars still continue a bit today. But people doing time domain kept insisting that it was much superior to frequency domain. Well, when we only had one or two modulation frequencies, they had a point. But when Enrico developed the true multi-frequency instrument in the mid-'80s, that was no longer true. But then the time domain people would say, but look, you can't subtract the background like we can. Because in the single time correlated single photon counting, I described how that worked. You could put in a background, maybe you have fluorescence in your buffer or background somehow, and collect that for a certain time, and then collect the sample for the same time and subtract channel by channel the background from the fluorescence before you do the analysis. Well, you can do this indirectly, of course, with the phasors. You can measure the phasors. In this case, we have a background, and you get the phase vector for the background. The sample in this case is N-acetyltryptophanamide, and you have N and B as the mixture. But then you have the sample, but you can then subtract using phasor algebra the background from the sample and get the corrected frequency domain data for the sample. And this was absolutely correctly corrects for this. So interestingly, years later, I discovered that Lenny Brand in 1993 had this paper, Ludwig Brand, his colleagues and friends called him Lenny, where they actually had this, what we would now call a phasor plot, to show how you could use this to study in the lifetime domain the binding, in this case, of calcium to Quin2, one of those calcium probes I mentioned. And they had not seen the 1984 review nor the 1991 paper, so their work was completely independent, and they never named their plot. And this was the only time they did this, but there's Lenny Brandt. But it's interesting that he saw the value of this rearrangement on his own, and Lenny was one of the great fluorescence people of the generation just before Enrico and I. He also was inspired by Gregorio Weber to get into fluorescence. So let's look a little bit at the phasors, borrowing a slide from Enrico. And Enrico is going to go into this in more detail also when he gives his lecture on phasors and FLIM. But the idea is you have this plot of G versus S, and if you have a single exponential decay, they will all appear on what we call this universal circle, okay? Now, if you have a mixture, suppose we have a mixture of these two components, they will appear inside the universal circle. And so any non-exponential term will occur inside, or a mixture of single exponentials. And if it's a mixture of only two components, then it's going to lie along the line tying these two together. And in fact, you can easily extract the fractional contribution of each component from the phasors. And here's a nice little animation from Lorenzo from the LFD, and he's going to be talking, I guess, later today or tomorrow. And I like this very much, this little animation. You can see on the right side, the phasor, as we start mixing in two components, A and B, the phasor point moves along the line joining them. And on the left, you actually see the two components, B and A, and B goes down, A goes up, and the solid line is the composite decay pattern. But it gives you the idea how when you add one into the other that you change the phasor. So I thank Lorenzo for this animation. Now, the phasor approach in fluorescence then had been around since '84, but was dormant for a while until several labs began to apply it to FLIM once in the new millennia. And these are the Andrew Clayton, Quentin Hanley, and Peter Vermeer, and Bob Clegg, and finally Enrico, as we'll see. And this paper by Clayton, Hanley, and Vermeer in 2004 came out. Actually, their point was to resolve two lifetime components in the film image given only one light modulation frequency, using the equations in Weber's 1981 paper that I showed you. And they never actually, so their point was quite different from modern phasers, as we'll see. They want to use this to analyze components. And they called in the next time they published this, they called it an A-B plot, which I must say is not a very interesting name. And they used data from previous film publications to resolve mixtures, but they never presented any film images. And there's Andrew Clayton and Quentin Hanley. And in 2005, Redford and Bob Clegg also made a plot they called a polar plot. And there's a picture of Bob Clegg. And they didn't present film images. They wrote that they've used film data and it's given them unique insights and added an interpretation. But the references they added were both the abstracts presented at 2003 meeting. And again, they never showed the film images. And so that was that. But now Enrico in 2005 introduced phasers, first in the fluorescence course in general. This is one of these workshops sponsored by ISS. And you can see Enrico there. There's Susanna in front of him, and there's me. And in 2006, and then he introduced this at his famous advanced workshops and then really went into details. And this was the first workshop, and he's been a point in every workshop since. I think there's 14 workshops now. Unfortunately, not this year. So he went into great details on this. But the method he introduced, this is important, was conceptually completely different from previous work. Specifically, as he'll tell you in great detail, he can connect with his method the phasers, the pixels in the film image to the phasor points that gave rise to beneath those pixels, and vice versa. So you can go back and forth, and that's an important concept. And this graphical approach quickly became a transformative tool in the film field. Now, over the years, I have to say, Enrico's always invited me to the LFD advanced workshops. Probably this was for comic relief. I don't know. But I think it was during the 2008 LFD advanced workshop, I was listening to Enrico expound on the wonderful merits of phasers, which I admit I never fully appreciated till then, even though I was on that review. And it occurred to me, wait a blankly blank minute, I could be doing all this in a blankly blank cuvette. You can see how I used to dress back then. And of course I had tenure then, so as a full professor, I can do what I want. And that happy thought kicked off a series of cuvette-based phaser papers from my lab. And I want to mention them because I think it's useful to illustrate how useful the phaser method is, not only in film, but in cuvettes. So after initial rejections of these papers, because from analytical chemistry, because the reviewers didn't think phaser method was of any value to anybody, they were eventually accepted by analytical biochemistry. We had 2 papers. In fact, we even got the cover of that issue, although it took me a while to find out, because when you look online, you don't see the cover. You have to actually go to the library and look at the journal to see the cover. And that was done by these gentlemen in my lab. Nick James was a postdoc with me, Justin Ross a postdoc, Martin Steffel was actually a graduate student from Czechoslovakia, from the Czech Republic, with Martin Hoff. And he came to my lab for 6 months from Prague, and I put him to work on our first phaser measurements. And this handsome young man is Felipe, who I think is in our audience somewhere. And he had a role in phasers in the early days, which I'll show in a moment. But one of the first things we did was take mixtures of 3 fluorophores, and here you see BENS, lifetime almost 30 nanoseconds, AEDANS 5.3, rhodamine 1.66, all single exponential decays. They're all on the universal circle, but when you mix them, as you would expect, you start getting Let's look at DNS and rhodamine. All the points of the mixture are along the line joining them, and the same for any combination. And when you mix all three of them, you get a unique point that depends on the fraction of each contribution. And in fact, it's easy in the lab to change the frequencies. The previous one was done at 20. Here's the same, these curves shown at 15 and 30 megahertz, and we see that they rotate around as you go to higher frequencies. Everything sort of rotates counterclockwise because obviously the phase shift and modulation depend on the frequency too. Now here's some work with that. Here's an example. If you look, this is actually from an early paper and even my thesis, I think. You get the intensity or lifetime profile of tryptophan as a function of pH. And because it's zwitterionic, when you protonate the amine group and deprotonate it, you have a big change in the lifetime. So you can actually get a phasor plot just doing exciting at 280 at 25 degrees, one frequency. At high and low pH, it's on the universal, and in between, it just runs along there, along the tie line between them as you change the pH. You can show this at any frequency. Typically, of course, what you do is pick the frequency that best shows the phenomena you're trying to illustrate. Here we see NATA, the tryptophan analog, this single exponential, being quenched by acrylamide. As we add acrylamide, the lifetime gets shorter and shorter, but stays single exponential. We go along the universal circle. Here's lysozyme, which has 6 tryptophans. It's inside the universal circle, but I don't care how many tryptophans, I get 1 point, and we see that we can go inside the universal circle, but to the right as we add acrylamide. Here's some other early studies. Dynamin, a protein I've worked on for years, has 5 tryptophans. Again, you get 1 point in the universal circle. When you add GDP, the lifetime properties of 1 or more changes in GTP, gamma S, changes again. Here's HSA, which is almost single exponential, but not quite. And when you add thyroxine or furosemide that bind, it also changes the lifetime. Notice I say monomeric because if you buy a mixture and you have the bottle of lyophilized HSA, you have about 50% of dimeric HSA in it. And I point that out because people have done studies they published on the lifetime properties of HSA straight from the bottle, and you can see the dimer is different from the monomer. You can isolate the two on a column. And this was interesting because we were presenting this, Nick and Justin and I, at a local biomedical symposium in Hawaii. Somebody came up to us and said, oh, didn't know anything about fluorescence, this person said, can you use this to look at interactions of proteins? And I hit my forehead. I said, my God, he's right. So here we see 2 proteins, antithrombin and lysozyme, each with multiple tryptophans, 1 point, phasor point. But when you add them together, whatever you mix is along the line. Here we see a point, the mixture. When you mix antithrombin and thrombin, which have multiple tryptophans, they do interact and it changes the lifetime. So you go off the line. So here's a way to see this without even having to label the protein. And here we see lysozyme. You unfold it with either guanidine or urine. We get quite different pathways. This takes us to the data of Felipe, finally, and he worked with the protein, bacterial fission protein called FITZ, and he put in single tryptophans at different locations, one at a time, and you would get the urea curve looking like this. Here's a blow up of that, and very reproducible, very specific patterns. And you can even make, which he did, you can make 3-dimensional plots for urea or guanidine, and you see the data in S and G, and then you can project that onto the back plane. But these are nice in 3D. You can rotate them and really see different regions along this unfolding pattern, and you see they're quite different for the two. Now, when we look at phasor plots, Bob Clegg pointed out, and this is one thing he did, that we see the lifetime of the donor in red does go down as you have energy transfer. I said you lower the lifetime of the donor. But if you look at the acceptor, you excite the donor, but look at the phasor points, the lifetime of the acceptor, it's outside the universal circle. This is what we call an excited state reaction, another phase delay. And that's useful. Here, and this is one of my favorite examples. You have FRED and GFP. And suppose the classic GFP has one tryptophan and the chromophore buried in the middle. I asked you, is there energy transfer from the tryptophan to the chromophore? How would you do it? You can't remove the chromophore or destroy it. But we can excite it 471 into the chromophore itself. Look at the fluorescence above 500. We see a single exponential no matter what the light modulation frequency. But when we excited 280, we're outside the universal circle. This tells us that some of the light is going to tryptophan, which is transferring energy to the chromophore, and instantly you can see there's energy transfer, and that was very, very difficult to do in any other way. And likewise, if you use Loredan, which you'll hear a lot about, and you put them into vesicles where you can get a relaxation, this again gives you points outside the universal circle. Here we see Lionel, some of the data he did in my lab, came to visit with his mixtures of surfactants models for pulmonary surfactants, or mixtures of lipids. So you can see these data points are outside the universal circle. You cannot analyze with just regular equations, but you can track them and follow trends by using these phasors. And postdoc Jose from Brazil came to my lab with peptides that interact with lipids, with micelles, as two tryptophans. Again, on the left, you see you get a point free and a point bound, and when you start mixing in the micelles, you'll get this titration. And here we see on the top right, C, we blow it up, and you see this. And actually, how do we go from that data to the binding isotherm? Well, you use Pythagoras' theorem. So I was very thrilled to finally use Pythagoras' theorem for something, since I learned it in high school. And when you convert using the distance along this phasor line, the concentrations, you get a binding isotherm. And the final example was our colleagues in Uruguay, Matias, Joaquin, Sebastian, and Anna, and some of them may be in the audience, wanted to look at the dilution, dissociation of a dimer and of a decameric protein into a dimer. And here they are, all the participants. And each monomer has two tryptophans, but we don't care how complex you can analyze the decay. Normally you would excite at 300, but we do it at 280. We don't care about tyrosine excitation. We just want to get a point. All we care is, does the point change when we dilute? And it does. And you see here at one frequency modulation going from 40 to 0.5, we get a nice trend. Actually, I thought that going below that, where it dips down below the line, was due to dimer monomer, but I'm told from my colleagues in Uruguay that this actually was due to the background not being so clean and pulling it over. In fact, you'll hear in Enrico's talk how autofluorescence in cells can show up in these phasor plots. And it's very easy to map the dissociation along the hypotenuse, and you can do these measurements very quickly in the cuvette. Okay, so again, back to FLIM, and as we said again, Enrico's software will plot pixels in the image to the phasor points, and that's what makes it so useful. And you'll hear a lot about, this is a famous paper from Enrico's lab where they looked at autofluorescence, anything that can give rise, and this is a composite showing where free NADH would appear, or some bound, or FAD, etc. So many different things put in one composite picture. So acknowledgement, certainly Nick James and Justin at UH for the early work, and Martin Steffel and Felipe, of course. And then we have the data with Jose, and Lionel from Uruguay, and all the other participants from Uruguay. And finally, of course, I have to thank Enrico, who gets a big mahalo for all his work over the years on this. So that's it for me. Thank you very much.
Great, Dave. Thank you for the talk. Very nice.
I will stop sharing the screen if that's all right.